right now. So as Jonathan said, I'm going to talk about free nilspaces, double-coset nilspaces, and Gowers norms. This is a recent work joined with Pablo Candela and Bala Segedi. And first, a little bit of introduction, although we have heard all these things before. But well, just to quick recap, there's the study of the Gowers norms. It started with the work of Gowers on Semeredis theorem. And then since then, the area has grown very fast. Here we have probably the most well-known result in the area, the Green-Tau theorem. And in this talk, we are going to focus a lot in the, well, a lot. One of the thing we're going to put the focus on is the inverse theorems. So as you can see here in the middle, the study of the inverse theorems have been classically divided into several cases. We have the case of finite cyclic groups, and this was achieved by a series of papers, Green-Tau and Ziegler. And then there's this other setup of vector spaces of characteristic P. And this was done also in a series of papers, Bergerson, Tau and Ziegler, and then Tau and Ziegler, and in several cases. There was indeed a very recent refinement, a qualitative refinement. And well, these things that I mentioned here are all qualitative, in the sense that these are the important results in the qualitative aspect, but there are also these more recent results of Gowers and Milicevic in the vector spaces of characteristic P, and of Manners in the case of finite cyclic groups. And even more recent, there's these two results that also they have appeared in previous talks. There's first this result of Jamneshan and Tau. It's a very general inverse theorem for the Gowers U3 norm. And well, the statement that I put here is very, well, it's informal, so there are more quantifiers. And in fact, this result is also quantitative. It has some bounds in terms of epsilon. But for this talk, we are not that interested into that, but about the statement that here it says you can take any finite group, you don't have to restrict to cyclic groups or vector spaces. This works in general and gives a correlation, an inverse theorem with a nil manifold, let's say a nil sequence. And there's also this other result, even more recent than the previous one, that in the case that you focus on finite abelian groups of some bounded torsion, then you have a result very similar to the case of vector spaces of characteristic P. And essentially, if a function has a large Gowers UK+1 norm, then it correlates with a phase polynomial of some degree bounded in terms of K and M. Okay, and so in parallel to the developments in additive combinatorics, there's the developments in ergodic theory. So in ergodic theory, there are a very important class of semi-norms defined by Host and Kra that are analogous to the Gowers norm in ergodic theory. Also, Host and Kra started an approach to these Gowers norms from an axiomatic point of view. They wanted to define this thing, the weakest structure a set must have, so that you can define a Gowers norm on it. And this was the inspiration of Antolin, Cameron, and Segedi to define nilspaces, which generalized the work of Host and Kra to any step. And then, well, the theory of nilspaces, as you have seen, has grown very quickly. You have, for example, in topological dynamics, there are the series of papers of, for example, of Goodman, Manners, Albarju that have a very interesting treatment of that. But again, in this talk, we are going to just be more focused on the inverse theorem. And there's this general inverse theorem of Candela and Segedi of 2019 that says the following. If you have any abelian group set, and then a function that has a large Gowers UK+1 norm, then you correlate with something, with this composition, W composed with bar phi, where bar phi is a morphism that goes from the abelian group to the nil space, and then ellipsis functions W. And well, clearly this this theorem looks very much like the ones that I presented before, but there was the problem of, okay, this is a nil space, this is a new definition, new axioms, and the question is, okay, can we give a description of these or some of these elements in terms of some more familiar objects or for mathematicians? And the answer is yes. And in fact, maybe one of the main results, or the main result of the paper and of this talk can be seen in this slide, which says the following: when you work with Fourier analysis, then this corresponds to studying the U2 norm. And in the U2 for the U2 norm, from the inverse theorem for the U2 norm, you need the harmonics are just characters. You have these functions that are here. You have a homomorphism, and here the complex exponential, and that's it. That will work. And it turns out that in higher order Fourier analysis, you have a picture like this, where instead of having R modulo set, you have this space that I don't call it abelian group because I won't treat it as an abelian group in general. There's just set to the R cross R to the S, modulo some gamma. This means that there will be some group acting on this space, and this this is the quotient by the action. And this is essentially what we want to prove, that we can see higher order Fourier analysis, and then in general, the correlating harmonics in the inverse theorem can be taken to be some guys like this. Now we are going to see these things more in detail. First of all, let's again come back to some more familiar objects like the Heisenberg manifold. The Heisenberg manifold has appeared in many works in higher order Fourier analysis. I think the first one was this one of Green and Tao. And it is defined as follows. You take the upper triangular matrices, you take the discrete Heisenberg manifold, so just with integer coefficients, and you take the quotient. We know also, Pablo mentioned it, that this can be proved to be a nil space. But in the approach that we want to show in this talk, we will see that this is totally equivalent to just taking R3, the space R3, and then take the quotient by the action generated by these two functions. These two functions that, as you can see, well, this clearly is just adding one, but this one has this weird thing here of summing x in the z coordinate. This is what will make it equivalent to the Heisenberg manifold. So in order to properly show what we are doing, not with just some strange gamma action, we have to make some definitions first. We have this definition here of a free nil space. Free nil space, well, first of all, Pablo has already introduced this notation of DI. You take an abelian group, and then you can create a family of nil spaces just by taking this filtration with the host Kra cubes. And all of these define perfectly valid nil spaces. And a free nil space is just consists on taking products of this kind by groups of the shape that we are interested in. So integers times some real numbers, and you take any combinations of those. Those are fine, by the way. Everything, AI, BI, everything is fine. Then we have this other definition that also Pablo has told us about, the translation group of a free nil space. This morally just corresponds to that given a nil space, you can define a group that respects cubes, that you can apply to certain cubes in some phases, and then they are preserved by that. It's a group. And the important thing, the two important things about this is the first one is that gamma will be a subgroup of this group. And the second one is that this group is easily describable. So, but instead of putting here the general formula, which is a little horrible, We have this kind of a small example. If you take D1 of Z, D2 of R, D0 of R, then the group translations of F consist of all transformations of this kind. So as you can see, there's a pattern here. In the first coordinate is this a D1, so you just add a constant. In the second one, you allow a linear phase. And in the third one, you allow a quadratic phase. Okay, and before going to the punchline of this talk, one of the most important definitions of the paper, we need a little bit more documentation. This given a free nil space, we consider this pi j, which for us, I mean, has also some deeper meaning in nil space theory, but for us is just projecting to the first jth factor. So this is a product from 1 to k, and the pi j just forgets about the larger degree terms. Just take it from I to 1 to j. And then there's this thing. This is the most important thing of the talk, maybe. And it says the following. Okay, a group gamma, we are going to call it fiber transitive group if it satisfies the following thing. Given any pair of points in the pre-nil space, imagine that you can go from one to the other using an element of this group gamma. So gamma of x equals y. And then also suppose that by some chance, these 2 points lie in the same fiber. So you haven't moved much in terms of the pi j factors. You have not moved at all. And then this condition, this fiber transitive group definition, means precisely this: that there exists some gamma prime in gamma, but also of the correct height of height j plus 1, such that it moves x to y. It is important that this is like an existence. The group gamma need not act freely in F. And here, as this is an important part, there are 2 small examples. First one, you take F to be this small, this free nil space, D1 of Z cross D2 of Z. You consider these translations that you can check that these are translations. And for example, as you can see in this last one, this one doesn't act freely. I mean, it's obvious because if you put x equals to 0, this doesn't move at all. But still, you can check that this gamma satisfies the fiber transitive group of the fiber transitive property. In fact, what I put here, this reference, is because this nil space that you will obtain at the end when you take F modulo this gamma is precisely the examples, the family of examples that Host and Kra gave in 2008 as examples of nil spaces that cannot be represented as coset nil spaces. Yes. Yes, it is for all years. Sorry, this is bad style of writing. This is if for any x and y and any j and any gamma you have this equation, then you have gamma prime. And the last thing, this is like a non-example. This is something that does not satisfy the fiber transitive property. And again, this is something that you can check by hand because it is a very small example. And in fact, it can be proved that the quotient of F modulo this gamma prime is not a nil space at all. But well, here we are not we are not interested in the minimal set or in the minimal definition such that the quotient will give a nil space, but just to note that, I mean, this gives a nil space, and if you don't put anything, then you may run into problems. Okay, then let's go back to the world of abelian groups, because it is good to have that in mind. One-step nil spaces are abelian groups. And for abelian groups, we have this result that says that, okay, any compact and finite rank abelian group can be described as Z to the A cross R to the B, this time as an abelian group, modulo a co-compact lattice. And what we do in this paper is precisely extending this to the world of nilspaces, replacing this set to the A cross R to the B by a free nilspace. And then this co-compact lattice will be a fiber transitive group. So any nilspace, any compact and finite track K-step nilspace can be represented in this fashion. And as a corollary, we get what I announced at the beginning, that combining this with the inverse theorem of Candela and Szegedy, we can get well, an inverse theorem where the factor object here is something much more explicit. It's just this free nilspace modulo a group action that is very restrictive and you can describe in some sense. Okay, so let's come back to also to double-coset nilspaces just to fill all the gaps in the title of the talk. As I remarked, the gamma is a group that acts on F, but is not necessarily a subgroup of F. But indeed, it is possible to turn this into a double-coset space. As I mentioned here, the idea of using double-coset nilspaces, double-cosets to represent nilspaces or some related objects like factors of some ergodic systems, this is not new. It has appeared before in a presentation of at least of Goodman, Manners, and Barju. And also we have a paper of Shalom where he uses it to describe, as I said, factors of some ergodic systems. And the trick for doing that is the following. In a free nilspace is just this product of sets and R's of different degrees. As you can do the following: you take, you pick a point, any point, then you take the stabilizer of a point. This is a subgroup, and it can be checked that F is isomorphic to this coset space. This, in this case, right coset. And then there's this theorem that essentially combines the knowledge that we acquired before. And if you have a free nilspace and a fiber transitive group action, then F modulo gamma equals this. This is not direct in the sense that these things acts by multiplication. This thing acts on the nilspace, but can be checked that this works. And you can represent any compact K-step finite rank nilspace as this. Okay, and the nice thing about double-coset spaces is the following. If you just take the fiber transitive property and you say, okay, how does this look like in a double-coset space? It turns out that there's a symmetric property that pops up, which is, well, symmetric in the sense that you can take any of these two that are, they are equivalent. And this is just the same as the predefinition that I had before, just adapted to the setting of double-coset spaces. And well, here there's this remark that also in parallel to the completion of this work, Jamnes and Shalom and Tao shared with us a preprint where also they were able to represent some totally connected systems of order K are represented also by coset nilspaces satisfying this definition. Okay, let's talk a little bit about topology. I don't want to go much into details with this, but just some things that are important to have in mind is the following. We will face the same problems for nilspaces as we face in group theory. So for groups, if you take R as a group, you take the quotient by Z or Q as an algebraic object without topology, those are perfectly fine cosets. But it turns out that when you add topology, this is much better than this one. And the same will happen with free nilspace. We will have to put some conditions in order to ensure that we don't run into this type of problems. First of all, there's this question of saying, okay, what is a nilspace which doesn't have a compact topology? Because as far as we know, this question has not been addressed before, that you say, okay, you have your nilspace with their axioms. And if it's compact, then you have this condition, the cube sets are closed. Okay. But on the other hand, when you drop the compactness, it turns out that this is not enough. Then we needed to ask for these conditions that, again, we don't know if it's optimal, but this is pretty and short. And this ensures that we get a nice theory of nilspaces. Here I put as a sanity check, we always have to think that, okay, what happens for one-step nilspaces, so for abelian groups. And then it turns out that if you drop this condition, you can have some weird thing that would be a nilspace that is not a topological group. So, and we don't want it. And finally, there's this huge slide that, again, I don't want to go much into detail because it's about many places where we had to do topological things. The important part probably is the slogan, that topology is important. We have to take care of it. It will help in many places. For example, the group of translations, we will only care about continuous functions. But on the other hand, it required us to develop a lot of tools that were available in other settings, but not in the non-compact setting. And these are just an example of those. But the philosophy is that everything works, just we have to deal with the topological part. Okay. Again, coming back to the analogy with groups, an extension of an abelian group can be represented in many senses, but one of the typical ones is with this short exact sequence. Then we say G is an extension of H. And well, this is equivalent to say you have a surjective homomorphism from G to H, if the groups G and H are sufficiently nice. Turns out that this setup is more appropriate for nilspaces, as far as we know now. And we have here this definition. This is an extension of nilspaces that this was not mentioned in the talk, so I'm happy that I included it in mine. And again, what you have to think of this is just this is the generalization of extension of groups, of abelian groups, in the setup of nilspaces. You have a function that is the extension function, and then everything works similarly, or at least we hope so. And again, we have here, coming back to abelian groups. So for abelian groups, we have this very nice property of groups of this type of set to the R, R to the S. And it's this property that is, well, it's called projective, but it just means that if you have a surjective homomorphism from G to one of these groups, then essentially G, provided that it is a Lie group, is essentially this group cross some other subgroup, some kernel. And here we have this is intermediate, but also like important result that says the following. If you have an extension of a free nilspace, it splits. So again, as you can see, this kind of shouts for, this is the generalization of this thing for nilspaces. You just change the notion of extension and everything works just as fine. As a corollary, we get a pretty little result that says the following. You take the Heisenberg group, and then you endow it with the Hoskra cubes, and you see it as a nilspace, so you don't care about its structure as a group. Then this is total equivalent to taking just this simple nilspace, a product of abelian groups with the different filtrations, but just a product of abelian groups. And this is the proof that it's only this slide. So I have tried to put everything here so that you can see it like from scratch. The proof of this result and of many results in this paper, at least, is by induction. Okay, and the idea is not new. In fact, I think the first place where I saw this is in our work of Szegedi about finite nilspaces. We use it also in another paper. And the idea is the following. First of all, recall that you have some extension map, this Q that goes from your nilspace to the free nilspace. First step is to prove that essentially, given any translation, any of these elements of the nice group that acts on the nilspace, it commutes with Q, commutes in this sense that if you take any translation and you compose with Q, this is equal to another translation composed with Q. And this induces a map from the translation group of the extension to the one in the free nilspace. The second step is to prove that this Q hat is surjective. And to do this, we use this criteria of translation bundles. that essentially boils down the problem to checking that some extension of the k-1 factor of f splits. And by induction, this is exactly what we want to prove. So this holds by induction hypothesis. And once we have that this is surjective, we just create a cross-section that is a morphism. And we do this very kind of manually in some sense. We take these translations that just add one in one coordinate. We take the one parameter subgroups. This can be considered as infinitesimal generators for the continuous coordinates. We need this kind of machinery. And then we lift them all. We can do this because, well, all of this will turn out to be Lie groups, and all this step can be done. And finally, we construct the cross-section in this kind of manual way of saying, okay, any point x can be represented as applying beta, so just adding the number of ones in every coordinate necessary, advancing the necessary steps in the continuous coordinates with a continuous argument, this q. And then we just take the lifted version, and this can be proved to be a continuous cross-section, and this shows that the extension splits. This is just the idea. And finally, I want to show the proof of the main result, that the proof that any compact and finite rank nilspace can be realized as a free nilspace modulo fiber transitive group action. But instead of doing this, so as I said here, what I'm going to do is more like following the approach that we followed when we were looking at the problem, is that we didn't have access to the definition, but instead we were like, okay, suppose that, I mean, for at least for abelian groups, there's some subgroup. Okay, what can we do? And so on. So in that sense, I'm not going to say, oh, this is fiber transitive, and by induction, we can prove the fiber transitive property. This is what is in the paper. But for the presentation, what we did was more following this scheme that's saying, okay, for the case k equals 1, we know that this is true. Okay. Then suppose that in the k-1 factor, there's some subgroup that realizes this property. So the quotient of fk-1 modulo h equals xk-1. So you go to one step less. And for now, you don't really know, we didn't really know what h was, what properties did it satisfy. Next, we do this, we consider the fiber product of the x and fk-1. This is just by definition this, just you take pairs in fk-1 cross x that agree in these maps. Next step just consists of showing, okay, if you have this subdirect product, you can prove that this is an extension of the free nilspace fk-1 by the last structure group of x. In fact, this thing, I think, was already in other papers. We had to do it again in this new topology, new non-compact topology. But at least the fact that it is an extension, the algebra part was already done. And so, by the result that we showed before, this splits. So this is perfect because this subdirect product is a very easy thing. It's just some free nilspace module cross some decay of some group, that this need not be set to something cross R to something. Okay, but what we can do is, again, go back to abelian Lie group theory and say, okay, you have this group set K, you don't know what it is, but we can cover it with a Lie group with some Z. And essentially, we form this new nilspace. This one is now going to be free. You just take the fk-1 and you cross it with decay of Z. And now Z has the correct shape. And again, well, and this is the diagram that realizes all that we have done up to now. Just take F goes, I mean, this phi just consists on taking in the second coordinate, you take the homomorphism phi. This is the isomorphism that we showed, and this is the rest of the previous diagram. And you say, okay, this is nice, but we don't want only this, we want some group acting and some quotienting. Okay. The way of seeing the original group in the new, I mean, lifting the action from here to here is as follows. So first of all, this H, we can assume that it is finitely generated. Again, for Lie group, this is true. So we don't, I mean, for abelian Lie groups, this is true. So that's fine. Then you have here the action on Fk minus 1. And the way of lifting it is this this idea of saying, okay, we know that all this action trivializes through phi k minus 1. So therefore, here you just see the identity. This doesn't really appear here. So we can take here the identity, and in this subdirect product, you can take the product of these two maps. So you in the first coordinate, you act by each side. In the second, you just do nothing. Is the identity. That's fine. Then you say, okay, oh, but this is an isomorphism, so this translation can be seen as a translation here. And similarly to what happened before, that I showed you the translation group of a free nil space, this is very explicit. We can describe these things in terms of polynomials, like with its binomial coefficients and so on. So we have here a bunch of HIs that are, well, not HIs, but the lifted version, this HI prime, that are written in terms of polynomials. And what we do is just saying, okay, but one by one, I can lift kind of the coefficients that there's nothing else but that. I lift it and I get a family of functions here, hi tilde, that lift hi prime, and that makes all this diagram commutative. And finally, there's this the final guys to the party that are the following. You remember that we have covered the last structure group of X by some set, that is, this is just set to something cross R to something. And the kernel of this is generated by some other elements. So we can say, okay, but these elements in set can be seen as translations in the free nil space just by adding them to the last coordinate. And the last step is this one, is just putting everything together. We just got a good guess of what would be the lifted versions of the HIs. Also, it makes sense to add all these guys because they respect the congruence and they are invariant. And then we put everything together, HI prime, the group generated by this, and then you check that this works. And essentially, the fiber transitive property is something that came up when watching these groups and saying, okay, what does this satisfy, and which property, is satisfied by these guys. And once you have a good guess, then you just put the proof in a real mathematical way, and that's it. It works. And yeah, this is everything I wanted to say. Thank you. At least for final abelian groups is relatively easy, because this I have to write it here because I don't have it in the slides. So as you said, that there's this the finite abelian group, then you go to this F mod gamma, right? And what does this look like? So the nice thing about finite abelian groups is that you can always cover them by some set to some power n. There's a surjective here, homomorphism. And then what you can prove is that if you compose these two maps, then this is a morphism from Zn to F. And as this is Zn, can be checked that if this is just the quotient map, like, I don't know, pi gamma, then you can complete this diagram and you have a map from here to here. And this one is totally explicit, this with polynomials. Those polynomials could have come from C. Ah, yes, 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 yes. And they have to satisfy this property, but yes, at least here, that's polynomial map. So the application that I didn't put it here, but the thing that we were able to do is that using this machinery, we were able to recover this thing. We were able to prove that for the two-step case, the two-step case is very particular. And then for the two-step case, we can recover this result, not with the quantitative bounds, only the qualitative, because this comes from some other results with ultra products. But in the qualitative setting, we could recover this result that for two-step case, you can use nil manifolds. Two-step. Yeah. Mm. Yeah, that's the other thing. Yeah, thanks. Is as you can represent all of these quotients by a double-coset space, you have an inverse theorem with double coset. Thank you.